Okay, let's start. So far we know everything that we need to know about electrostatics and van der Waals. Now, this is the basics of the DOVO theory, and it's very important because whatever you do, you can't run away from the DOVO interactions. You can do lots of other interactions, and I'm going to discuss the most important of them in this lecture. But you are always going to have van der Waals attraction, unless you specifically have some system where you match the refractive index. But that's something that's hard to do, and obviously not the usual case. And you can get rid of electrostatics either, because even in the cases where you would like to have a system without electrostatics, you're going to have charging in one way or another. So DOVO is really the background of everything that we do in colloids, for good or for not that good. From the viewpoint of nanoscience, actually it may not be that good because it decreases your ability to control the system. In this lecture, we're going to do something that's very important and discuss the interactions which are beyond DOVO. So we're going to focus on things that have less formulas and more kind of physical and practical importance. Before we do that, however, I would like to go back a little bit to DOVO and finish the previous lecture with some introduction to the new one. Now, beyond DOVO just means that we're not going to discuss electrostatic and van der Waals in these interactions, but the interactions that we're going to discuss today are very important, and they actually give us much better control in many cases over the system that we're going to study. Before that, however, let's go back and just remind ourselves what was in the DOVO theory. We have this wavy curve, which describes a variety of the properties of the system. If you remember, we had the secondary minimum, which is more or less something that's not very relevant to many systems. We have something that's very important, the energy barrier. And this energy barrier is actually the something which keeps, the world around us, the liquid world around us, from collapsing. We have the primary minimum, where the leading force is what? Van der Waals. Once you go to the primary minimum, the van der Waals is so strong that the particles stick together, and you have to really spend lots of energy in order to get them out of there. And if you remember, we had this dependence of how the energy barrier changes when you add electrolyte. The addition of electrolyte suppresses the electrostatic repulsion, so eventually there is nothing to keep the particles or the films or whatever you have in your system apart. Then if you put in lots of electrolyte, the system collapses. And if you remember, the parameter which describes essentially the energy barrier is this kappa, the inverse Debye length. If you remember again, the stronger, the larger the charge on the counter ions, the stronger the suppression of the electrostatic repulsion. So counter ions of higher charge, like calcium, aluminum and so on, are very much suppressing the electrostatic interactions. Now, what I have done here is I have copied just a description of a table from a book which just summarizes different types of electrostatic formula for electrostatic interactions. Now, in the previous lecture, we just derived the basic formulas. What I have here is these are formulas which people can use in any type of reality calculations. And of course, I don't want you to remember this formula, or I wouldn't expect you even to be able to do that, even if you try to. But there is one important lesson here, and it is that depending on the geometry of the system, you have a variety of approximations. So picking up the right formula is the trickiest part actually in this type of estimations and theoretical research. So depending now, you have, let's take the case of two spheres. You have two spheres at constant potential, two spheres at constant charge, two spheres at linear superposition, where linear superposition means what? Why do you call it linear superposition? What have we done in order to linearize it? Right. And in order to expand it, we assume that the potential is not that large. So this means two spheres at small potential, two spheres at superposition, which is a little bit better approximation. We didn't go through that. As you can see, anytime we do that, the length of the formulas, the complexity increases. But none of these formulas is something that you can do just by putting your parameters in a very simple calculational program and doing the calculations. The point to be taken is that whenever you do electrostatic calculations, the first thing that you need to do is really think about what approximation you're going to use. Large separation, small separation, large potential, small potential, spheres, flat surfaces, of course starting with the consideration whether you want the force or the energy and so on. Okay, so we know about this. And we discussed what happens when the van der Waals forces predominate. And these are these fractal aggregates where the particles just clump together and form some structure. Now there is a very interesting, albeit very imprecise, relation in the literature, kind of a phase diagram, which tells you what is the volume fraction of the particles that you can put inside the suspension, what is the strength of the interactions, and what is essentially the structure that you obtain in the case where the particles come together. I'm showing this not so much to give you something that's let's say the highest thought in colloid science, which it is not, but I'm showing this just to give you an idea of how the interactions relate to structure, relate to properties of suspension, and so on. So let's try to go through this. Very strong repulsion. The particles eventually repel each other very strongly. This was the image I showed with all those particles being far apart. You know that it's very difficult to do this experimentally because there are always counter ions coming from the atmosphere. Assuming that you can do this, however, you can see that actually the particles are not going to be suspended, which means freely moving around. The particles are going to repel each other and fill up all the available volume that they can do. So essentially they're going to form a structure just because they repel each other so strongly. Then you decrease the interaction a little bit so the particles don't repel each other. Let's say you're somewhere here. What this tells you is that you have a relatively large region where the particles can be suspended, where they can freely move around without forming some type of structure. So you're going to have just this milky suspension, for example, or whatever type. Now, in this case, you can, when you go to a very slightly repulsive interaction, you can get them to be to about 0.64 in volume fraction. Now, what happens even in this case where you go above 0.64 in volume fraction? The particles just get closed so tightly that they actually form some solid-like material, which can be also ordered. So eventually, if you want to keep the particles suspended, you don't need very strong interactions, but this is the usual case in practical systems where the concentration is about up to 0.5 and the interactions are not very strongly repulsive, but enough to keep them stable. And then if you go to the region where you have attractive interactions, what happens is again you can't put too many particles into the suspension. If you put too many particles into the suspension, they're going to clump together and they're going to form the structure that we have seen here. And this structure is actually not very closely packed. You have a small number of particles occupying a large volume, just because they are so loosely packed. Now, the description of such type of aggregates usually involves the concept of fractals and fractal dimensions. Some of you have probably heard about that. We won't go into details here. This is really an attractive concept, but not that usable from the viewpoint of colloidal engineering and what we'll be thinking about here. You can read this in the textbook, perhaps. The point is that these are very loosely packed particles. Now, what are the imprecision in this diagram? Now, what I have put here is that it does not distinguish kinetic and thermodynamic stability. Now, when I have put thermodynamic, I have put this in this way, which means that it's not real thermodynamic. Now, why is it not real thermodynamic stability? Let's say you are here in this region. Your particles repel each other. They are stable, but I kind of say that this is thermodynamic stability, but I mean, I don't really mean that this is true thermodynamic stability. Why is it not the true thermodynamic stability?
You can never reach thermodynamic stability.
Oh, no, you can.
So you can approach it, but it takes infinite length of time.
Right. Now, okay, I see some kind of like some surprise phases here. Now, from the viewpoint of thermodynamics, which is the stable situation for any colloid systems? Right, when they are aggregated actually, because if you think about that, the really thermodynamically stable case is this one, where you are in the minimum, absolute minimum of the energy. Luckily, however, for us, and for the existence of all humans, animals, whatever, the electrostatics keeps the things from just getting into this thermodynamically stable part, where everything is going to be collapsed and coagulated. However, if we assume that this is, let's say, kind of thermodynamic kinetic stability, then in this region, actually, the system is unstable intrinsically. If you wait for not that long period of time, even the particles here, which have been suspended originally, are going to eventually meet each other, jump into contact, and precipitate. So that's not really a very stable system either. So this diagram really doesn't distinguish the fact that, let's say, this part of the system is stable and this part is not. But again, I hope you get the feel here of how interactions, repulsion, structure come together in determining the properties of a colloidal system. Any questions so far? Okay, let's move on then. Now you know how to control electrostatics and van der Waals. Let's kind of define a couple of very general questions. Now, does the OVO theory describe the behavior of many colloidal systems? Obviously it does. It has been a great achievement in terms of understanding of colloids. It works well. It always describes the background interactions in your system. Now, then the question is this knowledge sufficient to describe the interaction in a colloidal system? And I have this non-smiley face here, because in reality you have many other interactions. And we're going to study the most important of these interactions today. And we're going to continue with some interactions which are specifically important for biological systems next time, in the next lecture. So, whatever you do, you should know that you always have van der Waals and electrostatics interactions. But then let's go to the interesting image here, and you can try explaining that, for example. This is again a system where the colloid particles have been organized; they are packed together. And in order to pack them together, what these Japanese researchers have done is to add polyelectrolyte. So the polyelectrolyte is the key in particles getting together and forming this and forming these crystals. Now, if you take a look at that, you can see that there essentially we have crystals, and next to the crystals you have area where there is nothing, no particles. Now this means that there is some attractive force which brings the particles together. And it's not likely to be van der Waals, because if it brings them together, they're going to aggregate in these fractal aggregates that we have seen before. The fact that they pack so nicely, and actually if you decrease the amount of polyelectrolyte, they're going to come apart, tells you that something brings them together, kind of compresses them into these phases. And it does this gently, and actually, as we're going to see, in a controllable manner. Now, what can this thingy be? Now, any suggestions about, maybe some of you have heard different types of interactions, so we can give a name of different interactions here. Or we can leave this as a kind of a mystery, which we're going to solve at some point later. I see Chris has some suggestions there.
Osmotic works. But the
Osmotic is very right, very true.
because the polymer can't.
Right, and the name of that force is actually depletion force. Yeah, we're going to, it's a force on osmotic effect, and we're going to discuss it right now. Now, Daniel had some question? Or?
What is a polyelectrolyte solution?
Polyelectrolyte is just think of some soluble polymer, which is very well hydrated. Usually it will form some kind of clumps in solution. But it's a very small polymer, just molecules around the particles. Okay, so then the issue here is that you have some small particles around these particles, and these particles are actually polymer molecules. So how could these small molecules, particles, affect and then change the properties of the larger particles? Now, and this is the key actually understanding, this is the key to understanding the system that we have here and many other systems. So this is, before we begin that, this is the lineup of all the forces that we're going to, most of which we're going to describe today. Right now you have to kind of take this as a roadmap of some just names: oscillatory, depletion, osmotic, steric, hydration, and so on. Now just let me give you the general concept of what these forces come about. Now these two forces, and you can see they can be repulsive or attractive, comes because you may have particles. Which are smaller than the ones that you study, or smaller than your film, and so on, but you have some particles here which induce some new interactions. Now these two forces, again, these are example of force which can be attractive or repulsive, comes because you have polymer. Or for that matter, this polymer can be a non-ionic surfactant, which is routinely put in many systems. Now you can say, well, I mean, we have, in a way, we know colloidal physics and so on, so we always have particles. Because even water it's not a real medium, it's made of molecules. So maybe the water molecules themselves can, just because they have discrete size, shape, and interactions, the water molecules can be the source of some type of interactions. And these are some interactions which are very important, especially for the origin of life. And these are hydration and hydrophobic interactions. And the specific interactions which are relevant to biological molecules are something that we're going to discuss next time. So let's start going through this schematic now. And first of all, check out what happens when you have particles. Now, when I say particles, I can mean even just water molecule. This can be any type of particle. Molecule, polymer, whatever type of particle you have. Now, what happens, let's say, when you have an interface? Well, when you have an interface, if you remember, we have been discussing that perhaps the boundary of the interface is a little bit smeared out, some molecules may be further out, some molecules can be further in, and so on. Now what happens, however, when we have an interface with a solid? And we have a very smooth solid, so it's on the scale of those particles, it's just a plane. Now obviously this first layer of particles here just is not allowed to move out of the interface. And then there are these other particles which kind of push them towards the interface, because everything we do here is in terms of motion. So the first layer of particles would be really pushed towards the interface, and then if we discuss what the distribution of the density of the particles is going to be as a function of the distance, which is called what?
Radial distribution function.
Yeah, I mean, like somebody who has taken my class should have said that, not Daniel who has not taken my class in thermodynamics. This is not radial distribution function really, but this is distribution function. So I have the distribution function, and actually this function has specificity close to the interface. So you have this region where you just can't have particles below 1 particle diameter. When you go to 1 particle diameter, you're going to have lots of particles because all the particles are really in that plane. When you go to 1.5 particle diameters, I mean, you may have some particle kind of protruding there and so on, but generally most of the particles would be a 2 particle diameter, and so on. And then when you go further out, I mean, this structure already gets destroyed in a way, so you just have liquid, disorganized particles. Now what happens then if we bring these two surfaces close together? At some point, this difference in the densities of the particle distributions are going to overlap. And we know from electrostatics that when we have overlap, we have something that's relevant to force. What could you say would be the origin of this force here? How would you name it? Chris likes to name forces. Come on, I mean, you gave me the...
Oscillatory force. I mean, that was...
This is oscillatory force, right? But I mean, again, the origin of this would be from what? Osmotic effect. Let me show next slide, and you have time for questions then. Now, suppose that we have this situation where we have the two surfaces without particles. We bring them a little bit further out, and then you have a single layer of particles. If you bring them further out, you can squeeze 2 layers, maybe you can squeeze 2.5, and so on. But if we superimpose this on the distribution of the particles, you're going to find out that let's say you're going to have no particles here. The concentration of particles here is very high. The concentration won't be that high in this case, for example, when you have 2.5 layers, because you just can't fit enough particles to pack them well. And then when you go further out, you just really... So what's going to happen is that you're going to have a force which say, okay, you say like, what is the osmotic pressure of these particles? 0. You have lots of particles here, very high concentration, high osmotic pressure. Again, you can't pack the particles well, low concentration of particles, low osmotic pressure. And because this compares to the bulk, so if you just plot it, you're going to have either lower pressure than the bulk or higher pressure than the bulk, depending on whether your slit fits very well 1 or 2 layers and so on of particles or not. If the particles fit well, then you have high osmotic pressure, which is repulsive. The surfaces are really repelled because you have lots of stuff between them. If you're further out, you don't have enough particles, you have lower osmotic pressure, which means attractive. And this is the origin of the so-called oscillatory forces, where eventually the forces go like that: attractive, repulsive, smaller attractive, smaller repulsive, even smaller attractive, even smaller repulsive, and so on. This even smaller comes from the fact that, if you remember, the further away the surfaces are, the less organized the system is in the middle. And if you don't believe that such forces exist, I'll have to find a movie and show it to you. it is amazing, but sometimes the systems can really go, they really form layered structures just because you have particles in the middle. You can actually use these particles as a means of keeping the surfaces in a film at some specific distance apart. And it just goes out until in layers. I just didn't have a digital movie which I can show you to you, but I'll be glad to tell you a little bit more about stratification, which was the area of research of one of my advisors. So stratification is actually an expression that we have this oscillatory force. We can immediately write the osmotic origin, very similar to what we did with electrostatics. The force is the density of the particles between the plates minus the density of the particles when the planes are infinitely separated. Now, it's very difficult to calculate this force unless you are from Keith Gavins's group. Somebody from Keith Gavins's group here? Yeah. So if you're in Keith Gavins's group, that's not Chris Gorman, Keith Gavins. If you're in Keith Gavins's group, you can do the molecular simulation and find out exactly how many particles you have inside.
What about Dr. Hall's group?
Dr. Hall does different types of simulations. Keith Gavins's group is really the one who does simulations of structuring of molecules. If you have seen one of his students actually, he has these nice images where you can see how they fit inside a pore, a slit, and so on. If you translate this into density, you can actually find the force which this organization induces on the colloidal system.
So I have a question.
Uh-huh.
So let's extrapolate this geometry so that we have some whole solution of little dots, which are the polyelectrolytes, and the surfaces of the latex microspheres.
Right.
If the polymers between the latex microspheres are lower than the bulk, they'll pull the latex microspheres.
Exactly. You're obviously in discovery mode today, but this is the so-called depletion force, which I'm going to actually show exactly what you kind of summarized here in a few slides from now. Now, this force, oscillatory force, is typically found between flat surfaces. When we have latex, usually, or other spheres, usually the curvature prevents the repulsive forces, unless you have really very high concentration of particles, but you still have this deep attractive minimum, which can be attractive. Now, just in terms of, you want to describe them theoretically and do some fitting. This is very difficult to calculate. So what people have done, of course, you can construct always a function which has this specific property of being oscillatory and then decaying at a distance. Now, the two functions from math that you know, the oscillatory function would be a cosine and the decay function would be an exponent. So people have just constructed this function which has this oscillatory component and decay component. Have put it inside the distance between the plates, normalized by the size of the spheres here. And you have your formula for oscillatory forces, which is not explicitly derived, but it is more an empirical approximation. If you remember in electrostatics, the decay length was the Debye atmosphere. In this case, the decay length is the diameter of the spheres. And then, of course, people have done some measurements of that. And if you don't believe in these forces, you would certainly begin to believe after you see this experimental data here. This is done by some of the people who have used these Raleigh separators. So that's why all the points that you have are actually in the repulsive mode. They have taken a molecule, some siloxane, which has exactly spherical molecule with a size of 10 angstroms, 1 nanometer. So you can imagine those small molecular balls between the surfaces, and then you start pressing them, and suddenly you start measuring when you go, let's say, below 10 molecular diameters. Now, 1 nanometer is exactly 1 diameter. So when you go less than 10 molecular diameters, you suddenly see that the force goes up, down, up, down, up, down. So suddenly, depending on where you are, if you're exactly at 1, 2, 3, 4, and so on nanometers, you have attraction. If you're at 1.5, 2.5, 3.5, 4.5, and so on, you have repulsion. And then the whole of it kind of slightly tilts downwards here, as you can see. Well, maybe you can't see because the pen wouldn't write, but you can see that kind of the average goes down. Now, why does it go down? Also, why did these oscillations eventually go in this direction? What's the key there?
So you get close to the wall.
And what happens?
It's
Brian here had some like what happens when you bring two particles close to walls?
Well, the force decays as you get away from the wall. So
This is the oscillatory force. Now, why, however, on top of the oscillatory force, kind of these oscillations go down here? Sure. I mean, you have van der Waals attraction between the surfaces always, right? That's what kind of, this is the background of DLVO. You may have oscillatory forces, but you would always have also the van der Waals force, which kind of goes down, right? So whether you like it or not, the van der Waals force is always going to be here and is going to tilt the system downwards.
that's the van der Waals force from the wall.
Yeah, between the two walls. So eventually, if you did not have oscillatory force, the force that you would measure would be something like that. Right? This is the van der Waals force. The oscillatory force kind of in a way modulates this force, but because the van der Waals force is always acting, you have this downward trend because the surfaces auto attract each other by van der Waals interaction. So that's why you need to know DLVO even if you use some other type of force. Now, so far so good, but you can tell me, well, it's an interesting exotic force, maybe useful in some thin film, and it actually can have some application. But then in my practice, I can't make much use of that force, especially if I'm interested in nanoscale engineering. Oscillatory force is kind of, I mean, right or wrong. I mean, can you make use of that force or not? Yeah, so our discoverer here, Brian, actually suggested exactly what can be done, and which is very much done these days. Now, this is possibly the most usable force in terms of engineering. If you want to make a force which is attractive, this is the best way to make an attractive force, because this is very controllable and usable force. Now, if you just go to this case here, the moment you don't have any particles between the surfaces, you're going to have the equivalent of osmotic attraction. Now, pay attention that this assumes that there is something on the other side, so the particles can actually have osmotic pressure on the other side, right? If you just take a thin slit, well, it's still going to work because you're going to have the osmotic force going to be the kind of pulling them out. So the point is that you have this tip minima. The depth of this minima is related to the concentration of the particles, so you need to have particles. But once you have particles, suddenly you are going to have this force where when you bring them close together, you suddenly have this deep well where the particles fall down, or the two surfaces fall together and stick together. This assumes that they won't stick because of van der Waals forces. Let's say you protect them a little bit, and we'll discuss this a little bit later. But assuming that they don't stick by van der Waals, you have made this kind of well where the particles drop down and they attract each other. And people who do theoretical estimations know that force that looks like a well is a good one because it's very predictable. So you have found a way to do a well. Now you can say, okay, I mean, again, how this relates to practice. This is how it relates to practice. If you take two latex spheres and you put something small, and this something small can be, in the simplest case, just be micelles. So you make a very dense micellar solution. You put two spheres and suddenly you find that the sphere starts sticking. you decrease the concentration of micelles and the spheres unstack. And the reason for that is that because the spheres come closer together here, there is a region where no micelles can actually get in that small gap. So you can think of this gap as being eventually an area on which you have the osmotic repulsion. The osmotic repulsion that acts on this side of the sphere, eventually bringing it closer. So you can think of this force. The way you can think of this force is that actually you have osmotic pressure on all sides of the spheres, but without this one here in the middle. So, I mean, you can think of this as osmotic force, you can think of this as osmotic force in this direction. The equivalent is that the spheres stick together. Now, related to the now let's think about the mystery image that I showed in the beginning. The polyelectrolyte in this mystery image is the particles. And this is why when we have added polyelectrolyte, the polyelectrolyte, which you don't see here, has been the equivalent of bringing all these particles by attractive force together. And this is again, like I want to emphasize that this is very, very useful force. Now, first of all, it can be strong. This is something that is not present to DOO, it's reversible. How do you reverse it? You just decrease the concentration of the small particles, or polyelectrolyte, or micelles, or whatever. In a way, you just add some water in the system, and then the particles spring free. You add polyelectrolyte, they aggregate. So this is a very basic, very important force in colloidal engineering. This force can allow you to be engineers. And I'm going to show this, and maybe one of you is going to tell us a little bit more about this. There were this group of researchers at the University of Pennsylvania who some time ago actually not discovered but took use of the fact that this force is going to exist also between a flat surface and a particle. So then this force is going to bring the particles to the surface. So far so good. Now imagine that you have something like that. A small pit. And you have this particle here. Now the interaction of this particle with that wall is going to be okay. I mean, yeah, it'd like to be there. But then if you put it in the pit, it's going to have all those three sides of the particles being free from the small particles. So that's where it would like to go. So the equivalent is now you make some microfabricated surface. You put pits on the surface or you put edges. You just can put an angle actually. Then you put large particles. Then you put small particles. And the large particles all go and organize themselves where you would want them to be. They're going to go, let's see if you have an angle like that, they're going to come here. If you have pits, they're going to go in the pits. You decrease the concentration of the polyelectrolyte or small particles, micelles, and the large particles can come free. You increase it again, they go there again, and so on. So this is one very powerful tool for assembly of particles onto surfaces, different types of structures, and so on. Yeah?
How big can those particles be?
The large or the small?
The large.
Well, they can be, let's say, I mean, roughly set any size you like them. They can be as large as bubbles. If you take the formable bubbles, actually, these two bubbles are going to stick together because you can expel the micelles from between the film and they're going to get stuck. The only restriction in a way of this method is that you have to have a large concentration of small particles. You can just put a little bit of small particles. You have to put a lot. That's why people use surfactants, micelles, polyelectrolytes, something that's benign enough and cheap enough, also inexpensive. Yeah.
Did we hear a student talk about, I think it was a gentleman there, super wet ability to try to crash out colloids down onto a surface instead of maybe around the perimeter? Am I getting that right?
Now this it was aggregating particles on the surface. That's how you can make super wet process. But this is not relevant to depletion in this case.
Yeah. Wasn't you trying to force the things down onto the surface?
In a sense, what I was suggesting is that instead of having a spherical cap that was my droplet, I'm taking that volume and distributing it over such a large area that the film is so thin that it evaporates really quickly and the particles can't diffuse or migrate anywhere.
So in his case, I mean, he may have considered again like concentration, slamming them against the surface and so on. But this is really kinetic effect. You just dry them fast enough so they get where you want them to be or something like that. Now in this case, you can just take, let's say, a surface which is typically made from semiconductor technologies with pits. You put large particles which would fit in the pits. You dump in small particles which can be just surfactant, micelles. So eventually you just dump some soap. And what happens is the large particles they're going to diffuse around a little bit, but the energetical minimum is going to be in the pits. Or if you have, let's say, some small kind of like angle or trench or something like that, they'll go in the trench. Actually, I'm going to show you some examples like that when you come to the colloidal engineering part. I just want to kind of turn your attention to this very important and useful force. Kevin had a question.
What would be the relative size of the particle? Not just a large or small. Do it
well, 1 to 10 will do typically in many cases. The real restriction is that you have to have lots of small particles. You may have to have the small particles being, let's say, 30 volume %. So it's not like just I'm going to add a little bit. I mean, you have to add a lot. But 1 to 10 would work. Actually, there is a way to calculate that. You have to calculate what is the volume where the particles don't fit. Now you can say, wow, okay, so if this is the case, I'm going to put these particles can be large, and then that will be cool. But this is not quite the case, because then you have to increase the volume fraction of the large particles. And then if you think, well, how about if I take these particles and these particles to be the same size? You're going to reach what's called jamming limit. Essentially, if the particles are the same size, they eventually attract each other, kind of freeze at some point, which is the jamming limit, which is about 0.64, just because you have so many of them that they kind of repel each other. But typically 1 to 10, 1 to 20, 1 to 50 would be about a good size. So it's a very useful, easily controllable force. Other questions at this point? Okay, let's move further on. Now, the people who have taken polymers classes can kind of like are excused from listening to the next slide. This is just some kind of very brief summary of polymer physics. Now, in many cases, in many systems, what you have is you either put polymer or you put surfactant in the system. And when you put polymer or surfactant for that matter, but polymer, now you can have two cases actually. You can the so-called grafted polymer, which be one which is chemically connected to the wall. Or you can have polymer which is adsorbed on the wall. So some of it will be on the wall, some of it is going to be kind of tailing away from the wall. These two cases, from the viewpoint of repulsion and physics are not quite the same, because you can see that the density of the polymer here is going to be larger some distance away from the wall, and the density of this adsorbed polymer is going to be larger at the wall itself. Now, just again in terms of polymer physics, the parameter which is basic in this case is the so-called radius of gyration. Now, if you put a polymer in suspension, this polymer is never going to float like that. It's always going to be, the thermal forces are always going to kind of try to make it kind of, like going to some kind of just conformation. Now, however, this polymer, unless it hits the suspension, not going to make itself a knot, right? Because it in a way has osmotic repulsion in itself. Now, the so-called case of ideal solvent does not mean that we have a solvent which dissolves it greatly. This means that this solvent essentially has no interaction with the polymer that you dissolve inside. So the polymer is kind of in a way in a vacuum state in terms of interactions. The radius of gyration of such a polymer in ideal solvent is defined like that. L is the length of a chain and of a unit of a chain, and 10 is the number of units of a chain. It tells you that the radius of gyration is going to be some fraction of the length of the extended polymer. So this is the preferred size. So let's say like this one, which is not fully extended but not fully collapsed iron. Now, when you have interaction between this polymer chains and the solvent, you are going to have that the chains, if the chains love the solvent, they're going to extend, kind of maximize their contact with the solvent. This is like if you like what you're doing, you really would like to do it a long time, and if you don't like it, you would like to finish it fast. So the chains are going to be extended in the solvent. The relation between the radius of gyration and the so-called Fourier radius, which describe the radius of the polymer in an arbitrary solvent, is this coefficient here. I called it interaction coefficient. In Izraelashvili, it's a coefficient of the extended chain and so on. The point is that it gives you the interaction contribution between the radius of gyration and Fourier radius. If the polymer likes the solvent, it has favorable interaction, it's going to extend. If it does not like it, it's going to collapse. Now, this is the formula for the fully extended chain. And from the viewpoint of colloidal stabilization, now what we're interested in, we put surfactants to our colloidal systems, or we graft polymers on the surface, or we put polymers which adsorb and act as surfactants. Now, what's going to happen is, if we have these polymer covered surfaces, and if we try to bring them closer, the polymer is not going to like it, perhaps, especially if it likes the solvent. Pushing two surfaces with polymer on top, close to each other, is going to be the equivalent of really desolvating them. If you push them too close, you're going to really extract the solvent out of it, and you're going to have this polymer on its own, which it's not likely to like. But it depends. So this is the origin. Again, like you can think of this as osmotic origin. So whatever you do, it's osmotic kind of element. You can think of this as osmotic origin, just you have osmotic pressure of those chains. And because of that osmotic pressure, they wouldn't like to be pushed together. The bottom line is that you're going to have strong repulsion between the surfaces. And this can be really strong. This can be much stronger than any other repulsion that we have in colloidal science. So from the viewpoint, again, we think about engineering. If you want to keep something stable, you don't try to increase the electrostatic interactions to the maximum. What you try to do is you try to coat it with a grafted polymer layer. If your polymer likes the solvent, your particles are going to be stable forever. And this is all called steric repulsion between the particles, or steric force. Just a few expressions here. What happens when we have low surface coverage? Again, don't people like to use exponents? You have again the distance between the surfaces. And in this time, the characteristic decay length is the radius of gyration. Again, you have these 1,000 formulas with all types of parameters and so on, and you say, oh, I don't like them too much. But you can see that physically you always have something that's very simple. In electrostatics, you have an exponent where you have the distance scaled by the Debye length. In oscillatory forces, you have an exponent, the distance scaled by the size of the particles. In steric repulsions with polymers, you have the exponent, the distance scaled by the radius of gyration. So you always have something physically which immediately kind of just allows you to understand what's going on. And it's usually very simple constant. Now, what happens in high surface coverage? This is the so-called brush layer. I mean, the particle, the chains repel each other too, so they would like to be extended. This is a formula proposed and then extended, actually, used by Huygens, which is one of the Nobel laureates. One of the few Nobel laureates related to colloidal science. Gamma here now, in your write-ups, I forgot this stop here. This is not the word no, this is number of grafted chains per unit area. So gamma is the surface density, and RF is the Fourier radius, as we defined on the previous page. And then, if you do lots of calculations, you can derive this formula for the relation between the repulsion, the surface density of the chains, the distance between the surfaces, and the length of the brush layer. So, in principle, you know how to calculate the pressure between these surfaces once you know all those parameters, including the Fourier radius and so on. Now, note that this formula inexplicitly includes the interaction between the chain and the solvent. How does it do that? This formula, where are the interactions included here? Fast thinking award here. How do the interactions enter this formula? Interactions, huh? Exactly, yeah. The Fourier radius was, but you're not getting an award because you have listened to the polymer class. The Fourier radius includes the interactions. So the fact that we have Fourier radius in this formula, which goes through in the length of the brush chain, tells you that the interactions are going to be included in the formula. So again, just let me summarize, this is very important. If the polymer loves the solvent, it's going to keep the surfaces apart. Now, what happens if the polymer hates the solvent? Would like to kind of clump. What will happen in this case? Huh? Yeah. No. That's I'm going to show some results like that. But depends on the distance. Yeah. Yeah. I'll show you. I'll discuss this case. I mean, the basic answer is it can also put them together. But so far, I mean, it repels them. It wants to keep them apart. Any questions? Huh?
Yeah. What is the radius of gyration? Like, how do you physically interpret it if you have a wall and a surface and a polymer?
Let's say like that. Now, you put your polymer in theta solvent, ideal solvent, and the polymer really doesn't feel it doesn't have specific interaction with the solvent. It just does what it would like to do by thermal forces. And you have eventually the kind of a couple of forces acting together. The thermal force would like to stretch it out and kind of move it around. On the other hand, the entropy would like to have it all around the place, right? Entropically, a straight chain is not an entropically favorable configuration. So the polymer is really going to kind of like adopt different configurations, and the thermal motion is actually going to eventually, it can be extended, then it can collapse, extend again. You can imagine, like, it's going to just jump around the place.
Gyrate around.
Right. I mean, it is going to also rotate and move all around and so on. Now, if you just if you take a snapshot of the polymer while it does that, you can do this in time, or you can take many polymer molecules. And then if you determine the mean radius of the polymer globule at this point, this is going to be the radius of gyration. So this is kind of the average size of the polymer globule, which is determined by the the fact that it wants to stretch out by thermal forces, or it wants to collapse and adopt many different kinks because of entropy. But from the viewpoint of physics, is this really a very useful way to normalize everything? Because you need something like KT, for example. You need to have something against which you compare. If your polymer now, see, if this is the interaction parameter. Now, if your polymer, you put it in polymer in solution, if it extends above the radius of gyration, then this means that it loves the solvent. If it collapses below the radius of gyration, this means that it has the solvent, it would like to be on its own. The polymer would like to stick to each other rather than interact with the solvent. Let me actually show some experimental results. Now, the formula from the previous page in this range of parameters can be approximated by exponent. In this case, we have, again, like this is a little bit different normalization, but you can say, well, in the region between 2 times the length of the brushes, because this is already about brushes, so it's not just single polymer chain, 2 times the length of the brushes and the distance between the particles. In this range, it's going to be exponent, and people have done measurements. You can see that this is actually a logarithmic scale. So if this formula is obeyed, then it's going to be approximately linear. And you can actually see that the theory very much describes what we see. So this is a simplified formula, but you can see that it can be quite useful. Now, it's a little bit difficult to estimate the value of this force here, the way it's plotted. Actually, this is energy, the way it's defined. Force, but it can be enormous. I mean, trying to compress 2 grafted polymer layers is a very difficult thermodynamic task. So, if you graft something like a water-loving polymer on your particles, they are going to stay stable forever, as long as the polymer is there. If you use surfactant, the surfactant, like non-ionic surfactant, it acts like a polymer. The hydrophobic parts of the non-ionic surfactant absorbs on the particles, and the hydrophilic actually is the chain around. Now, there is a little bit of a difference, however, because surfactant can desorb. So if you try to compress it, the surfactant may decide that it's thermodynamically easier for it to kind of go out rather than repel the surfaces. And this happens only at high compression. And now again, like terms of like award for fastest thinking and correlation, what was the equivalent of something similar which was tight about electrostatics? If you remember, when we have discussing electrostatic, we discussed
the constant potential and constant charge.
Right. I mean, like you to share the word here, the constant, the relation between constant potential and constant charge. If you have constant charge, which means that the charges on the surface stay there when you bring them closer, then the repulsion is actually going to be above what theory predicts. If you have constant potential, which means that some ions can get out, then the force is going to be smaller. So in this sense, there is another reason why grafted polymer chains are also more effective, and this is because they are further out. But for all practical purposes, just using surfactant, large molecular weight non-ionic surfactant stabilizes your particles well enough if it absorbs. So if you want to have engineering, if you want to have repulsive interactions, and you want to make sure that they stay repulsive, you put in steric stabilization. And one final slide about this. Now, what happens if the polymer chains hate the solvent? Now, they're going to kind of collapse on each other. So, a chain which loves the solvent is going to be like that, for example. A chain which hates the solvent is going to be kind of collapsing on itself. Now, this chain is going to be very much repelled from another chain here. Now, this chain, however, if you bring another chain close, they're going to kind of, in a way, feeling kind of like sympathy to each other in their misery in being in that solvent they hate. They're going to stick to each other. But this is going to be until the point where you compress them so hard that they already have osmotic repulsion within themselves. So what happens in this case is actually, if you take a polymer like that, you have this repulsive minima here. But then if you try to bring the surfaces even closer, they're going to start repelling each other because you're really pushing them too hard and trying to compress the chains too much. So there are interesting relation between how people attract and repel each other, but I mean, I guess you're going to kind of deduct them yourself, so let's move on. Now is the time for question, and actually what I have done here is this is a kind of a class workup exercise, which is we have all those different types of polymer-induced interactions and so on. So now you can try explaining to me what happens here and why do we have these different types of interactions. And of course you can also ask questions. Do you have a question or? Okay, let me then, if you don't have questions, then I'll ask. Now what is this case? This is the case that we just studied in the previous slide. You have good adsorption layers on the surfaces, not too much polymer around, and so on, so the particles actually repel each other. Okay, now we didn't study this, but somebody may try to explain why this may happen. When you have a little bit of polymer only, not too much. Yeah.
What?
It gets absorbed on both surfaces. Now imagine that you have this polymer which loves the particles. But you put just a very, very small amount of it. So this polymer is not enough to actually cover the particles and repel them. So what is going to happen then is if another particle comes close by, it may stick to this particle too. Just because if you put a lot of polymer, it covers them all around and it repels. But if you don't have that much, you can just have one molecule of polymer. Two particles would really like to stick to that molecule. And this is called bridging flocculation. This is actually used quite a bit in industry. If you have heard of different purification processes or separation processes which use polyelectrolyte. Like for example, in many cases, this is specifically for paper industry. In many cases, in paper industry, you add polyelectrolytes, right? Actually, the way you add polyelectrolytes, they adsorb on the fibers and bring them together. So this is an example of bridging flocculation, which means that you shouldn't put too much electrolyte because then again going to start repelling each other. But I mean, bridging industry, people routinely put some polyelectrolyte and then you have eventually all your fibers separating and you can process them nicely because the polyelectrolyte would bridge the fibers. Now, what is this? Did we study this case or not?
Yeah.
Right, and that would be?
They don't like the solution.
No. This will, in all those cases, let's say let's say this is the case where they like the solution. No, something else. It's said here. What is this for?
In the top one, they like the solution, right?
In the top one, let's say they like the particles better than the solution.
But now they like themselves better than.
Well, no. What happens here is actually this sequence goes when you what happens when you start adding more and more of the same polymer. So you add just a tiny bit of polymer, and the particles start sticking together because the polymer kind of glues them. This dealt some specifically hyped colleagues refer to this as nanoglue, but I guess there isn't much relevance to nanoscience this here. So you add a little bit, they stick together. You add more, they get covered on the surface, and then they repel each other. Now you add a little bit more of polyelectrolyte, they really covered as much as they can take. And then you see what?
Micellization.
Different
So the particles cause a depletion.
Right. It's not really micellization. If you use polymer, the polymer is going to be in itself is going to form globules. So the radius of these globules is the Fourier radius. This is the adopted radius because it kind of like has some interaction with the solvent. But the point is you have those small globules, you have those large particles, and to discuss the depletion forces, which come because small particles tend to push the large particles together so they can have more free area. Now, just a note to the depletion interaction, some people think of this as an entropic interaction. In the way of the small particles pushing the large particles out of the volume, so they have more volume to be entropically kind of like in the lowest entropical state.
Kind of entropic interactions?
This is depletion interactions. We discussed this in terms of osmotic just because the small particles can get in here. Now, theoretically, however, you can treat it, you get the same result. If you say when they bring those two particles, the small particles bring the large particles together, the small particles have more volume where they can spread around and adopt different configurations, maximize the entropy. But because thermodynamics is really powerful science, if you really do the calculations, you arrive at exactly the same result. Entropy being equivalent of osmotic force. Essentially, osmotic force is what? It's a force which the ions want to get further out because they can maximize their entropy. I see a little bit of confusion here, but I mean, the reason for the fact you have osmotic force may be entropic. The ions don't want to get too close. Anyway, now, and then what happens is, okay, we go back to our experiment here. Now we have added polymer. At first the particles precipitate together. Then we added more polymer and the particles dispersed. Then we added more polymer and the particles aggregated again. And then we add more polymer and the particles disperse again. Now what happens here?
Polymer balls got bigger.
No, not really. What happens is you have so many power balls here. Maybe you can go even better, but you have so many power balls that when you go back to oscillatory interactions, you can't even go to the minima because just the repulsion when you have one layer, for example, of balls is so high that they cannot even get together. This is really an extreme case. So, okay.
I have a question.
Uh-huh.
In the first case, what about the static hindrance between the two, like between the polymer chain itself?
Well, you have only one molecule typically in bridging.
One molecule of
Yeah.
what? Of the
Of
polymer?
Yeah.
Or just one chain,
Yeah.
you mean? Oh,
Right.
okay.
Yeah.
Because if there are more
It's
than
written, the way it's shown here, it looks like more, but typically you have bridging when you have one polymer kind of like sticking together two particles.
because if there is more than one, they would like to distribute themselves over the particles in such a way that they avoid static hindrance as well as cover the particle too, right?
Right. It depends on the size of the polymer. Typically, polymer is much more than the particles. So even two polymer molecules may not be enough to cover them, right?
Yeah, but they wouldn't be in this configuration. They would be on the outer side of them because they would like to
Maybe,
avoid.
Yeah, maybe. I mean, like in principle, the point, however, is that in many cases you have favorable configuration when the polymer sticks to two chains, to two particles.
Can you make sort of a web using that, the bridging population?
A web?
If the particles repel and the polymers repel each other, but not the solvent and not the particle?
You mean in the sense use bridging population as a means for making a structure?
Yeah.
That is tough because what's going to happen is the particles are going to stick in some specific configuration. I mean, like they're going to form a fractal structure essentially. When you have repulsion, if the repulsion doesn't really make them stick too close, like what's the osmotic, they can order. But with bridging population, it's not that easy. Now, on the other hand, however, bridging population is actually fairly useful. This is one way to glue the particles. Now, imagine you make some structure, and then you want to stabilize it. You add some polyelectrolyte which sticks to the particles, not too much. And then these two particles stick together, and the polymer is really bridging them very hard. There can be polymers like that. Very kind of sticky polymers. When you do that, you can actually stabilize the structure that you just made by adding the polymer. So in terms of colloid engineering, bridging populations can be very useful, but really as a glue. This is the way to kind of glue two particles together after you have put them in the place where you like them. Up to the extent that, as I was telling you, some people refer this as nanoglue. But I mean, this is really old-fashioned colloid science, actually, rather than some nanoscience area. If you have any question, now as I was about to tell about hydrophobic interactions, they're important for biomolecules. So we're going to study this next time. We're almost out of time. We have 1 minute only. So time for 1 or 2 questions. Yes?
In this word, like depletion speculation, you talked about small molecules. What are the small molecules here?
Polymer.
They're
Right. I mean,
okay.
the point's like that now. We put a very small amount of polymer.
Right.
It's only enough to now the polymer, the first thing what the polymer would like to do is absorb on the surface.
Okay.
If you put a very small amount, it's just enough to absorb on the particles and bridge them eventually because it's kind of sticky. You put more polymer, it absorbs on the particles and stabilizes them. When you put more polymer, it just cannot, there is no place on the particle where it can go. So the more polymer that you put, it just stays in these globules with Fourier radius, which act in this case as small particles which bring the large particles by depletion forces.
Okay.
And if you put so much polymer that you really have kind of all this filled with polymer, the particles are not going to stick just because they cannot push the polymer out of the way, that kind of repel all the molecules in the middle. So kind of if you understand how this works, you have really understood all the forces that we studied today. There is one more or a few more important forces which relate to biological molecules. Very strong, very important, which we're going to study next time until know almost everything there is to know about interactions. But so far, let's finish this lecture.
Important lecture.